So hello everyone, we are back to our plasma class again. So what we are starting in these days is two fluid model, and we were deriving the species conservation equation from two fluid model. What we did, we started with the plasma kinetic equation, and then we uh, took different order moments like zeroth order moment. We told that we will be getting the mass conservation equation, and the first order moment we will be getting the momentum conservation equation, and the second order moment we will be getting the energy conservation equation. So at present, actually, we are at the zeroth order moment, and we are trying to get the mass conservation equation. And there we defined the number density as indication of the distribution function over the velocity space, and velocity of the fluid element as of species S as 1 by ns, and then this is the indication of velocity over the distribution function over the velocity space, and this will give you the velocity of the fluid element at the location x at time t. So with this actually we started, and then we defined different quantities like mass density, summation over the species, and basically here we consider two fluid model. One is your electrons, another is ions, and in case you are having a partially ionized gas, in that case you can understand that this I will not correspond to only ions. You have to include the neutrals, and in case it is having some very high temperature, so it will be including the double ions as well, and that way we will calculate the mass density, that is the sum over mi ni, that is I will include all the species, but here we are considering only two fluid models. So one is your electron fluid and the other is ion fluid, and you are summing over them, and because the mass of electrons are very low, so you are basically getting the sum over the ions only as far as the mass is concerned. Then you are going for the charge density, so you have to sum over all the ions and the electrons, and this is what you are getting over there. Then center of mass fluid velocity you are defining like this. Current density is our conventional current density that we used to use in our electrodynamic classes, that is J is equal to NeV, and you are summing over the electrons and ions as well. And pressure, you know that it is additive for you have to consider all the species. So P is equal to, here it is electrons and ions when you consider the partial pressure of them, and then you just add them up. But if you are having multi-species, obviously you have to consider partial pressure of each of the elements. So total pressure is sum over the Pi, range over all the species. And here we are using only two fluid models, so we are summing up like electrons plus ion pressure, that is the total pressure. So what we obtained there, then we, as we promised that we will be taking the zeroth order moment to get the species conservation equation. So we started with this Boltzmann kinetic equation, and this is the collision term, which is bit problematic for us because we don't have enough knowledge about this collisional mechanism that is happening over here. However, for the species conservation equation, we are able to tackle this collisional term in a bit elegant manner, and to a very good approximation we could say that this dV, when you are integrating del Fs del T over collision, then this term was basically telling you the change in the number of particles within the phase volume over time and when you are averaging that out. So on an average, some particles are coming within that element and some particles are going out. So on an average, it was having more or less a constant number density. So this term we were putting as 0, and it is a really good approximation when a plasma is in steady state. So then what happened, this there are other two terms. One is this one, dVE, and then grad V of Fs, and the other one was V cross B, then grad V of Fs. And what we did actually, we integrated them well, and what we found that this term dVE grad VFS, when you integrate over the velocity space, then it is resulting in only the distribution function, which goes to 0 at both the limits, plus minus infinity. So this integrand was naturally 0, and when we came to handle this dV V cross B and grad VFS, it was a bit tricky, because if you want to really split it into components and want to do the integration, it may take several pages of your notebook to actually find out the integration value. But here we have done it in a very smart way, that you have noted that V cross Bi really doesn't have any Vi components, like I have shown here, that V cross B ith component is Vy Bz and Vz By. It is really not containing any of the x components. So when you are integrating our del Vx, so you can well include it within that, because it is not having any Vx component, so it will not bother at all. So what we did actually, we have taken it inside the derivative, because it is not having any, this part is not having any Vx ith component. So we are safe to take it inside, and when you do, we can take the integrand out. Again, because this Fs is there and Fs is going to 0 at both the limits, so it was giving us 0. So it is a very nice thing, no? So we are very smartly integrated this one to get the value of the integrand, and we could put the value 0, and then, as I told you, that it was important to model this collision term, del Fs del T C. This was, as I told you, that when we were considering a steady state, and this integration is taken, it is basically changing the number of particles per unit time, and that is basically 0, because some are coming in and some are going out. And you can say, like in this room, we do have average number of density at any corner of this room is more or less constant, so this part can be taken as 0. So to a very good approximation, we could make this part 0, and we could get these expressions, and then we multiplied this by Mi and this by Me, and then we added up, and then we went back to our basic definition of your mass density and your center mass velocity, and then we just put it over here, and we get that this is the mass conservation equation. So here we are, and then what we did actually, we want to go back to other equations like your charge conservation equation and then current contained equation from here, from the zeroth order moment itself, and then we will go to the first order moment to find the momentum equation, and then you will see that the complexity of mathematical derivation is increasing rapidly, and that is why we will not go for the second order moment for the this thing for energy equation. Rather, what we will do, we will derive some phenomenological expression for the energy conservation equation in fluid model, and that will be more insightful, and at the same time it will be avoid the complexity that we require for the mathematical derivation. And then what will go, we'll have a complete set of equation for the fluid model that will include your mass conservation equation, charge conservation equation, current continuity equation, then momentum conservation equation and energy conservation equation. You will see that this forms a complete set of equations. Basically, they will form the standard Navier-Stokes equation, including the electromagnetic terms which are appearing only because the plasma is a current carrying fluid, which normal fluid like water is not. So that is the difference in the Navier-Stokes equation for normal fluid compared to the plasma fluid. So that also is having an excellent behavior, and you will see the beauty of those equations, and we'll go into that. But before that, what I feel that we should go back to our plasma kinetic equation and put some more insights on the high frequency electrostatic waves in plasma that we initiated there. And I feel that the mathematical complexity was a bit more, and that probably hindered understanding the insights that is lying there within those equations. So I feel that in this lecture, what I'll do, I'll deal a bit elaborate manner and will try to bring the insights that is lying within the high frequency electrostatic waves, that is the Langmuir waves, okay, which we already studied, but we will study in bit more elaborate manner. So what we are finding here, that the dispersion relation for Langmuir waves, basically they are sometimes called electron plasma waves because we are considering mostly the electron terms, and the ions are more or less stationary in frame of the electron kinetics, because electrons are much faster compared to the ions. So the dispersion relation, basically what they describe, actually they tells how the frequency of these waves depends on wave number in a plasma. So Langmuir waves are high frequency electrostatic oscillation primarily involving electrons, and the dispersion relations gives you how the frequency of the wave changes with the wave number. So for a cold collisionless homogeneous plasma, we started with the Blasov equation, and we have ended up with this kind of dispersion relation. Okay, so for long wavelength limit, you know the relationship between this wave number and the wavelength. So long wavelength means very small k, and in that case this second term, that is the thrice k square into v square, that is really small. In that case omega is of the order of omega e, and you can say that the wave is almost non-dispersive. That is what we are expecting, that if we disturb a plasma from its charge neutrality a little bit, then the plasma will start to oscillate and try to recover the charge neutrality. So in that case it will oscillate with a frequency of omega e, but when we did a bit elaborate derivation of these waves, of electrostatic waves in plasma, we found that it is not really omega e, the non-dispersive relation, but it is added up with the term thrice k square and v square, which actually the dispersion depends on the wavelength, so through k, and the temperature of the plasma through VE. So VE is nothing but half mv square equal to kTs, that is the thermal speed of the electrons. So for shorter wavelength, when this k is large, the dispersive term really becomes important and the frequency increases with k. So you can now understand what is the significance of this dispersion relation as far as the wave propagation in plasma is concerned. Now the mathematical derivation part was a bit involved, but it is really not. If you follow it closely, you will find that it is very interesting as well actually. So there is a beauty in this mathematics, and if you follow it very carefully, you will find really able to explore the beauty within this. So we started with the Blasov equation. So right side term was a collisional term, and we just put that 0. So this is the total derivative, and we put this Fs as Fs0, the steady state solution, plus Fs1, small perturbation in the electric field, in the number density due to the perturbation. And when you put that, you know that because this is the average quantity goes out, only the oscillating or varying component stays there, and you are getting this equation in terms of this your varying quantity Fs1, and here you are getting this equation, and there is one QE into del Fs1 del T, you put that 0. This is because it is a second order term, because E is a small quantity and del Fs1 del T also a small quantity. So when you multiply these two, it becomes a second order quantity, and you can put that as 0. Then what we tried, actually we tried a plane wave solution like this, and when we put that, it's a simple integration, simple derivative rather you are taking over here, and then when you put that, you just get this expression for this perturbation. Fs1 is equal to minus I into Qs by Ms omega minus Kbx E into del Fs0 by del Vx. So this is the expression for perturbation for the electrostatic waves. Now what you see, that this S stand for species. So when you are considering a two fluid model, then this S once will be for electron, next time it will be for ions. So that is exactly what we did actually. So it is a general expression. It is equally valid for the electrons as well for the ions. And for ions, what we get, we get a minus Qi by this thing. And for electrons, we get this negative side out to sign out, because Qe itself is negative. It is basically the E. So we will definitely put Qi equal to Qe is equal to E, because we have already taken care of the charge over here. So in later on, we will just interchangeably use Qi equal to E and Q equal to E as well. So then what we have to go for this Poisson's equation, and when we apply this, Ni minus Ne gives you the charge density, and Ni is nothing but your Fi1 and Ne is nothing but Fe1. So if you take the difference, then you get the charge density, and divide by epsilon to make the equation valid. And then what you are getting, just simply substitute this over here. Simply take this expression and put it over here, and you are getting this equation. So it is not at all a complex, although it looks like a complex equation. And you know that the rules for integration under differentiation sign. So when you go this for this integration, you take care of that, and you can put this in terms of this. Now one thing you understand, that what we have derivative with respect to dvx, and we are integrating with respect to dvx dy dvz. So because dvx is there and you are integrating our dvx, so this dvx term will go out, because we are considering a perturbation in the x direction only. So the dvx will go out, and then you will get everything in terms of this dvy and dvz. Okay, this is so what we are getting, this is gvx, which is within this integrand, and what we get over here, a compact form of this dispersion relation, that is 1 plus omega square by k square. Then what I will write, actually dvx the whole integrand, what we got over here within this red rectangle, that I just write as gvx. Why it is vx? Because it is already integrated over dvy and dvz. So whatever will be coming here, it will be in the term of vx only, because vx will be left. You have integrated over vy and vz. So what you are getting over here is gvx. And what is the expression for gvx? That is exactly what we kept there in the inside that red rectangle, and this is what is gvx. So what we get, a compact form of the electrostatic wave dispersion relation, and that is 1 plus omega square by k square integration of 1 by omega by k minus vx dvx gvx dvx. Now you will be in a situation that what to do in this equation, and it is a complex mathematical equation. It doesn't give me any information about how the wave is going to behave, but actually that is not true. You have to look at gvx, and then you see that if you want to get any insight about gvx, then you need to know that f I v. So this is what? This is a distribution function in the velocity space, and we need to have an information about that. And you will see that in most of the processing plasmas to a fast approximation, we will be going to the Maxwellian distribution for this f. So if we here also will go for this Maxwellian distribution, and we will be able to find out the exact form of GVX. That is the purpose, because until I know this exact expression for GVX, I will not be able to extract any information about this dispersion relation. So to understand what is the value of GVX, I need to know what is the form of this distribution function. And as I told you, the distribution function in most of the cases we will be taking the Maxwellian distribution. Here also we will be doing the same thing. Then what we did actually, we took this as the distribution function. You can see it is your well-known form of this Maxwellian distribution. And you can now write this for plasma in a more meaningful manner, because in a plasma we are interested in the connecting this temperature with the velocity, and Vs is the thermal speed. Then I am just connecting through this relation, this fast in the box, white box, half mv square is equal to kT. So when I do that, then we are writing this Maxwellian distribution in terms of Vs. You see that we have just replaced this kT with mvs square, and we are getting this expression. So we are getting this distribution function in terms of the thermal speed and Vx, Vy and Vz. This thermal speed is dependent on the temperature. More the temperature, higher is the thermal speed, and this is a constant value depending on the temperature, and this is corresponds to the distribution function. And again you are seeing that it is expressed in terms of Vs in the exponent. So now we are in a position to expand this GVX through this integration. So what is this GVX now? GVX is equal to me by n0 mi. Okay, so how I am getting? I am coming back over here, me by n0 mi. So this one is there, this is the iron term, and this one is there, which is the this is the electron term, and this is the iron term. So I am writing both. The first one is the iron term, and the second one is your electron term. So this Bs is for species, and there will be one Bs for the electrons and one Bs for the ions. So I have just written it over here in terms of the ion thermal speed and the electron thermal speed. Now you must be already thinking that this Vi, the thermal speed of the ions, are much less compared to the same for the electrons. That is quite true, and we will be using this approximation also in the later things. But right now we are stumbled on this expression, how to integrate this one. Now as I told you, it will be integrated over dVy dVz. Now you are in a very clear situation how you can integrate over Vy Vz, and the expression will be in terms of GVX, in terms of Bx. So earlier you are a bit confused how this is coming in terms of Bx. Now you see that I told you that it will be integrated over dVy and dVz, and the resultant expression will be left in terms of Bx square only. And to do this integration, you can do it in n number of ways, but one very convenient quick method, I just use the polar coordinate. So this is Vy and Vz, and if you are writing this in terms of C, then you can do this integration very quickly, and it is coming as 2Vs square. So you just put that over here for this ions and for these electrons, and you get an expression in terms of Vx, Vi and Ve. This is the expression for GVX. Now we are in a position that to understand and to get a deeper meaning of this GVX, and we will now try to understand what the GVX means actually. Now you see that GVX is having two parts. One is your ion part, and another is your electron part. Now it's a mathematical quantity. If you just forget about the physics behind, then if you want to plot this, because this is a function of Vx, you have some Vi, you have some Ve. Okay, so you can just blindly make a plot of this one. But if you want to do so, you really need to know what is the Vi and what is the Ve in this case, whether there is any weightage on, not whether there is any relative importance of this term and this term as well. Now you see that this expression extends from Vx is equal to 0 to Vx is equal to infinity. When you do Vx is equal to 0, you see over here, then this term is simply 1, this term is also simply 1. Okay. Now it all depends on what is 1 by Vi and what is 1 by Ve. So depending on the temperature, you know that Vi will have some value and Ve will have some value. Now when this you are considering any normal posing plasma, this Vi is much less than Ve. So when this term is not there, just Vx is equal to 0, so this term is 1, this term is 1, it is 1 by V and it is 1 by Vi and it is 1 by Ve. 1 by Vi, because of the Vi is low, it is much higher compared to 1 by Ve. Okay, because V is quite high at any normal temperature of the posing plasma. Now if that is the case, then this is, you see that it is weighted by Me by Mi. So although Vi is small, it can be a large quantity, but it is multiplied by a factor who is Me by Mi, that is 1 by, if you consider only protons, then 1876 kind of factor is appearing over here, and then you can understand that this will be appreciable, not very large. Okay. Now when Vx is not 0, when Vx is not 0, then Vx is some appreciable value like here or here, you say, then what is happening? Because this Vi is small, so this is going to be a very high negative value. Now this is exponent and its negative of the negative value is very high, and here because V is large, so it is now reducing this negative exponent. Okay, so because it is negative, you know that algebraic 1 by x fall much slower compared to exponential of minus x. Okay, so that is how this term will be much higher compared to this term. Okay, so apart from Vx very close to 0, where you are able to maintain exponential part as nearly 1, rest of the places this term will be dominate very high because of two things. One is this factor Me by Mi is there, another factor, this Vi is very small, so this exponent is very high, negative exponent, so this goes to a value which is much lower compared to this term. So compared to the this term will be negligible in most of the places, and as you can see, the second term is dominating and showing its own only presence, except this very close to Vx equal to 0, where you are getting a tiny hump. So otherwise this was a distribution like this, a smooth distribution. This is added up with a small contribution from the ions near Vx equal to 0, and that is causing this part. So if you are in a location beyond this Vx equal to 0, then what you will have, you will be dominated by this term only, and you can well handle with only this expression. So that is Gbx is equal to 1 by root 2 pi into V exponential of minus of Vx square by 2V square, and this part you can just neglect there. So that is exactly what we will do in our later derivation, and we will just neglect this part and we will take this part only. Okay, so that will be there, and we'll be back in our next class in that. So this much now. Thank you.